Good day, class. In this final lesson today, we're going to look at a few word problems or applications. These I've taken right from your textbook. So my hope is that I can go through the 4 applications with you. The types of problems we're going to focus on are the related rates problems and the applied maximum minimum problems that we've already studied earlier in the course. But now, of course, we are including transcendental functions. So let's look at this first one. It's from exercises 27.4, and it is problem 19. It says, and there's the associated image, find the time rate of change of the horizontal component T at x of the constant 46.6 Newton tension shown if d theta by dt is 0.36 degrees per second, and evaluate for an angle of 14.2 degrees. Okay, so essentially this is the diagram. We've got this constant force of 46.6 newtons inclined at an angle theta. And we know that theta is increasing at 0.36 degrees per second. We would like to know the rate, therefore, that T at x is changing, and it is the horizontal component of that force. So you might remember that for any related rates problem, there are going to be 2 quantities that are changing with time, and the time rate of change of one of these quantities is always given, and the time rate of change of the other must be determined. So in this case, the time rate of change that we are given is right here. It's d theta by dt, and it is equal to 0.36 degrees per second. We're trying to find the time rate of change of t at x. So that's what we are trying to determine in this problem. So essentially, we need an equation that links theta with t at x. So looking at the picture, and since t at x is the horizontal component, you likely know that t at x is just 46.6 multiplied by the cosine of theta. That's how you find the horizontal component of 46.6 newtons inclined at theta. Okay, so if you're not remembering where this comes from, it comes from the fact that this, of course, is a right triangle right here. And so the hypotenuse is 46.6 newtons. This lower side here is certainly considered adjacent to the angle theta. So the cosine of theta then is the adjacent side, t at x, over the hypotenuse, 46.6. So that's where this relationship comes from. Okay, so now what we would do is differentiate each side of this equation with respect to time, right? We want to take the derivative of each side of this equation with respect to time. So on the left side, that simply looks like this. Now on the right side, first, we differentiate this with respect to theta, and then we would multiply that by d theta by dt. Okay, so what is the derivative of this with respect to theta? Well, of course, the 46.6 remains as the constant, and as for the derivative of cosine theta, it is simply negative sine theta times 1. Okay, so what we get right here is negative 46.6 times the sine of theta. Okay, so now we're pretty set. You know, you would think that you could substitute 0.36 right here for d theta by dt. And as for the value of theta, you would think you could substitute 14.2 degrees. But in fact, there's one catch when you're working with these angular problems. The angles must be measured in radians. So this currently is 0.36 degrees per second. We have to change it to radians per second. And how do we do that? You multiply by pi and you divide by 180 degrees. Okay? That's how we can change from degrees to radians. So 0.36 divided by 180 is 2 milli, okay? So we have 2 milli times pi, and this would be radians per second as desired. Okay, so that's the equivalent d theta by dt, but in the appropriate units for these types of problems. So that right here will be substituted 0.002 pi, which, I mean, it would be the same as substituting this number if I actually do multiply 2 milli by pi. I just prefer writing it this way. Okay, and so in addition though, theta must be substituted in radians. So why don't we say here, at theta equals 14.2 degrees. Okay, but again, we're going to change it to radians in the same way. We're going to multiply by pi and divide by 180 degrees. You see that in doing so, of course, the degrees would cancel. Same thing here. Okay, and then we end up with radians. So let's do the 14.2 divided by 180. Okay, so that's this number right here, 0.078 repeated. Pi. Okay, so I'm going to write it like that again because it's a nice way to write it, but it's the same as this number. So if I multiply by pi, it would be the same as this number as the angle in radians. Okay, so this is now the angle in radians. So when the angle is equal to this, now we can work out the time rate of change of t at x. So we do negative 46.6 times the sine of 0.078 repeated pi. And then we multiply that by this time rate of change, which is here, 0.002 pi. Okay, so I'll have to put this into my calculator correctly, I guess would be key here. So actually, maybe I'll take this number 46.6 and multiply it by the 0.002 first, okay? So 46.6 times the 2 milli is now this number. So now I have negative 0.0932 pi in front of the sine function. Okay, so all I did was I multiplied the numeric parts together. And then I'm just going to put this into my calculator now. So I'm going to go just left to right. I got to make sure I'm in radians, which I am, okay? So I'll put that there so you can see it. So negative 0.0932 pi times the sine of, I think I'll use a bracket to be safe. So it's 0.07. I'm going to put lots of 8s. I'll put times pi, and I'll close the bracket. So this should be my answer here. Okay? And then I'm just going to round to 3 significant digits. So I will write down negative 0.0718 as the numeric part. And now for the units, I need units of tension over units of time. And the tension in this problem is given by newtons, and time was measured in seconds. So what did we determine? We determined that as the angle increases at this time rate of change, the horizontal component of tension is decreasing at this rate. Okay, so that was an example of a related rates problem using transcendental functions, and we'll do another one. Okay, so here is a second one. Now this one I made my own picture for because there wasn't one in the textbook. So let me just, I'm avoiding the sun again, or actually, I'm not avoiding the sun again. Okay, anyway, so this is from the same exercise, problem 26. It says, a car passes directly under a police helicopter, which is 150 meters above a straight and level highway. After the car has traveled another 20 meters, the angle of depression of the car from the helicopter is decreasing at 0.215 radians per second. What is the speed of the car? Okay, so I tried to make a picture to accompany this problem. So I have the helicopter here, and at a certain instant, of course, the car is directly under that helicopter, 150 meters below it. But it is traveling in this direction. So this side length is increasing as the car travels. And I labeled that side length X. Now, when they talk about the angle of depression, they mean the angle here. Okay, so here's the helicopter, and this is meant to be horizontal. So this is considered to be the angle of depression of the car, and of course the angle there would be the same as the angle here, and this is a right triangle. Okay, now this is another related rates problem, so I'm going to start exactly as I did in the last problem, and that is by determining which time rate of change we are given and which time rate of change we must find. Okay, so here's the given time rate of change. The angle of depression is decreasing at 0.215 radians per second. So we are given d theta by dt, and it is negative because it is decreasing, 0.215 radians per second. Now, luckily, it's already in the correct unit, okay? So we don't need to worry about that. Now, what are we trying to find? What is the speed of the car? So remember, the speed of the car will be the time rate of change of x. Okay, remember we worked on this in an earlier unit as well. We said that velocity is the derivative of displacement. Acceleration is the derivative of velocity. Okay, so when we want the speed of the car, we want dx by dt. At what rate is x changing? All right, so now what do we need? We need an equation linking the two quantities, theta and x. So to do that, we can use the fact that this is a right triangle. So for the angle theta, this side is opposite and this side is adjacent. So that means the tangent of theta is equal to 150 divided by x. Okay, and to make this easier to work with, I think that, well, actually we could do it this way. We could bring this up and make it x to the -1 and then differentiate both sides with respect to time. But what I did instead was I isolated x, and then I just thought that that might be easier since that's the rate of change we're trying to find. So I did this. I said that x would be 150 divided by the tangent of theta, which means it's 150 times the cotangent of theta. Remember, the reciprocal of tangent is equal to cotangent. I'm going to move the phone. Sorry about that. So here we are. 1 over tangent is the cotangent. Okay, so now I'm going to differentiate both sides of the equation with respect to time. So on the left side, we will have dx by dt. On the right side, of course, we will have the constant 150, and we multiply it by the derivative of cotangent of theta. The derivative of cotangent theta is negative cosecant squared theta times 1. So this is negative 150 times the cosecant squared of theta. Okay, but that is simply the derivative with respect to theta. So of course we have to remember that that will be multiplied by d theta by dt. Okay, just like that. Okay, and again, that's because this part right here, if you like, this is just the derivative of x with respect to theta. So we have to multiply it by d theta by dt. Okay, same thing with the last question. Right here, this part, this is the derivative of t at x with respect to theta. Then, after multiplying it by d theta by dt, we end up with the desired time rate of change. Okay, so now I think we're pretty set. We know that right here will be substituted negative 0.215. And then all we need to do is figure out what we're substituting for theta. Now, did they give us a theta value? I think not. In fact, instead of giving us a theta value, they gave us a value for x. It says after the car has traveled another 20 meters. So they've given us an x value. So before we can substitute, we need to work out what the value of theta is. Okay, so let's do that. We'll say when x is 20 meters, then we get this. The tangent of theta is 150 over 20. So we should be able to work out the theta value in radians. That would correspond to this. So how do you get the theta value? Well, you'll take the tangent inverse of this 150 over 20. So again, calculator has to be in radians, and you go shift tangent, and then 150 over 20. Okay, so that's the correct angle there. So this was the tangent inverse of 150 over 20. And it's roughly 1.438 radians. Maybe I'll put one more number there. Okay, radians. And now we're going to substitute into this equation. So dx by dt is negative 150 times the cosecant squared, in other words, times the cosecant of 1.4382 radians squared times d theta by dt, negative 0.215. Okay, and of course, we can simplify this by multiplying 150 by 0.215. And that's 32.25. So we have 32.25 times the square of the cosecant of that angle. But one problem is that we do not have a cosecant button on our calculators. And so what does that mean? We have to use the reciprocal function, which is sine. So this is equivalent to having the sine of that angle squared down here. Okay, and now we can work out our answer. And again, I'm just going to round to 3 significant digits. So we're going to do 32.25 divided by, I'm going to say the sine of 1.4382 squared. Okay, so that's our answer. It's roughly 32.8. And then we need an appropriate unit, and unit for x divided by a unit for t. So in this case, x is measured in meters, time is in seconds. So this is the speed of the car, 32.8 meters per second. All right, so there was a lot to that question, but the key was, which rate are you given? Which rate are you trying to find? Come up with an equation linking those two variables, so linking theta and x, and then differentiate both sides of the equation with respect to time. And then at that point, you've solved it. You just need to know what value will we substitute for theta. And here, of course, is where you would put the given time rate of change. Okay, so that is example 2. All right, I think maybe what I'm going to do is stop this video and then start a second one for the two maximization and minimization problems. Okay? Okay, so let's do that. Quick pause.